Hi everyone, this is a stock 2020 talk for the paper An Improved Cutting Plane Method for Convex Optimization, Convex-Concave Games, and its Applications. My name is Haotian Jiang, and this is joint work with Intat Li, Zhao Song, and Sam Wang. So the problem we study today is the following feasibility problem. Given the convex set K, which is a subset of Rn contained in a box of radius r, our goal is to either compute a point in K or prove that K does not contain a ball of radius epsilon. The information of K given to us is via the following separation oracle. In particular, when we query the separation oracle with a point x in Rn, if x does not belong to the convex set K, the oracle outputs a hyperplane that separates x and K. We'll be a little bit more careful what separate means in the next slide. And if x belongs to K, then the oracle would output yes. In this case, we're done. So this is basically the feasibility problem. While it looks simple, standard reduction shows that the feasibility problem is as general as the optimization problem. Now let's look at separation oracle more carefully. So recall we are given the convex set K, which is a subset of Rn. We'll use SO to denote the time per oracle call. So for any query point Z in Rn, if Z belongs to K, the oracle would output yes, as in the following picture. If Z does not belong to K, it will return a separating hyperplane such that the entire feasibility region lies on one side of the hyperplane. And in particular, we can shrink the search space for the feasibility region by removing the other side of the separating hyperplane, as is shown in the following picture. That's why these methods are called the cutting plane method. Our main result is the following. We show that there is a cutting plane method which makes n-log kappa calls to the separation oracle and an extra runtime of n cubed log kappa, where kappa is nr over epsilon, where n is the dimension, r is the radius of initial polytope, and epsilon is the accuracy. So recall we want to either compute a point in K or prove that K does not contain a ball of radius epsilon, and that's the epsilon here. So now let's compare our runtime with the previous cutting plane method. The first cutting plane method is the ellipsoid method in first row of this table by Shor, Udin, Nemirovsky, and Kachayan. This method makes n squared log kappa calls to the separation oracle with an extra runtime of n4 log kappa. The number of oracle calls is later improved by the inscribed ellipsoid method to n log kappa. And this number of oracle calls of n log kappa is, you can prove that it's tight. But the actual runtime of the inscribed ellipsoid method is slightly worse. In 1989, Vaidya made a breakthrough using the volumetric center. He achieves number of oracle calls of n log kappa with an extra runtime of only n to the omega plus 1 log kappa. So this runtime is not improved essentially until like 2015. So Li, Sitfor, and Wang, using the hybrid center cutting plane method, they have a extra runtime of n cubed log kappa cubed. And our method is based on the volumetric center of Vaidya with a fast lever score maintenance data structure. And we achieve, so compared with Vaidya, we improve their extra runtime from n to the omega plus 1 log kappa down to n cubed log kappa. So recall omega is roughly 2.373 at the moment. And we improved Li, Sitfor, Wang's cutting plane methods runtime from n cubed log kappa cubed down to n cubed log kappa. So why is this second improvement important? So why is this log kappa squared important? So in some applications in computing market equilibrium, epsilon needs to be taken as exponentially small. And when epsilon is exponentially small, the factor log kappa translates to a polynomial factor in n. And that's, in that case, this log kappa squared is a polynomial as a quadratic term improvement. And moreover, we believe our actual runtime of n cubed log kappa is tight. So now let's start by introducing a very simple version of Vaidya's algorithm. So the algorithm always maintains a polytope that contains the feasibility region K, which is initialized to be the box with radius R. And so we also initialize Z to be the center of the polytope, where Z will be our query point for the separation oracle. The algorithm runs in n-log kappa iterations, where in each iteration, for each one of the constraint I, the algorithm computes a score for that constraint I, which is dependent on Z. So roughly the score measures how important each constraint is. The larger the score, the more important the constraint is. So geometrically, the score is just high levelly measures how far the center is from each constraint. So if all the scores are at least some constant delta, then the algorithm invokes the separation oracle at Z. If Z already belongs to K, then we are done. Just return Z. If, on the other hand, if Z does not belong to K, the separation oracle would give a separating hyperplane, which is a new constraint, and the algorithm will insert it into the polytope. On the other hand, if some constraint has very low score, smaller than delta, which means it's not important, then we just remove that constraint from the polytope. And in either case, because the polytope has either one more constraint added or one constraint removed, the center, which is the approximate volumetric center, is updated via Newton's method. Okay, that's basically the entire algorithm. So now let's see what's the runtime bottleneck for this algorithm. So in the algorithm, the constraint matrix A, which defines the polytope, is changing over time because their constraint added or removed over time. But for simplicity, let's assume A is fixed over all iterations. And for a vector W, which is for a vector W, we'll denote capital W as the diagonal matrix formed by the entries of little w. So for each one of the iteration, we need to compute this quantity P of W. This is a projection matrix onto the range space of square root of W times A. Roughly, it's the size of the matrices for this projection matrix is illustrated in the following picture. And W here is some function of the center Z. Roughly, it's like something depending on the slack of the center of the constraint with respect to the center Z. So score I of Z is just the ith diagonal entry of PWD. These are called the leverage scores. And because in each iteration, only one constraint is added or removed, so Z is changing slowly, and therefore W is also changing slowly. The bottleneck of Vaidya's method, let's think of M equals to M is linear in N, which is always satisfied by the algorithm. The bottleneck of Vaidya's algorithm is to compute this projection matrix PW. So the inverting the matrix in the middle, A transpose WA, already takes into the omega time. And given this inverse, given this matrix A transpose WA inverse, computing this inverse, the product of this inverse with A and A transpose on the left and right also takes into the omega time. So that's precisely the reason why Vaidya gets n to the omega plus 1 times log kappa, because each iteration one need to pay n to the omega time and their n log kappa iteration overall. So what is the hope for improving the runtime? So now let's abstract out the key problem here. Let's call this a maintenance problem. So we are given a fixed matrix A and a sequence of positive vectors W1 to Wt, which is m-dimensional, and m is linear in N, which is always satisfied. So we are promised that Wt changes slowly. I'll be a little bit more careful what this means later on. So recall PW, the projection matrix, is defined as follows. And here capital W is the diagonal matrix formed by the entries of the vector little w. So the goal is to either to output a sequence of vectors v1 to vt such that vt approximates wt coordinate-wise, and the projection matrix at vt is also approximation to the projection matrix at wt. So if we want to, so in the case of linear programming, the projection matrix is accessed in the following way. So given a vector h, which is the gradient, then one only need to compute the projection matrix pw dot h. So this is a matrix vector multiplication. This problem is the is called projection maintenance, and it's the central problem in improving the running time of linear programming recently. And in our case, in the case of cutting plane method, what we need is to maintain the diagonal entry of the projection matrix PW. So we call this problem the leverage score maintenance. So let's briefly recall the recent result of Cohen, Lee, Song on projection maintenance. So if we assume that, so in their case, the vector W changes slowly, meaning that WT plus 1 minus WT has L2 norm at most a constant, as most a small constant. So under that assumption, they can maintain maintain a vector V, which is a 1 plus minus 0.1 approximation to W coordinate wise, and they can maintain obtain a data structure that that when queried with vector H, output PV.H in little o of n squared time. So of course, there's some slack one can play with using with these parameters. So for example, one can make that error 0.1 to be something like 1 over polylog n. And also one might want to output the entire matrix PV as opposed to just answering queries like PV.H. But the running time of these modifications might be more than n squared. So one natural question one might ask is, can we already achieve leverage score maintenance using projection maintenance? Why is leverage score maintenance harder? So first of all, the guarantee we need for leverage score maintenance is an L2 guarantee. So let's say sigma is a diagonal entry of the projection matrix PW, and sigma tilde is our approximation. So what we need is that the difference between the error of our approximation has L2 norm, at most a small constant. On the other hand, projection maintenance only gives an L infinity guarantee. Second difficulty is that we need to really achieve the very tight n squared time per iteration. In the case of projection maintenance, one only needs to answer queries like PV.H. This is a matrix vector multiplication and can be done easily n squared time. So the difficulty there is how you get little o of n squared time. But in our case, maintaining the leverage score, which is the diagonal of the projection matrix, might take omega n squared time. So to see like why projection maintenance doesn't work here, even if we take the error epsilon to be n to the negative 0.01, which is far from achieving the L2 guarantee, this already takes omega n squared time to output the diagonal of PV. So how do we approximately maintain the leverage scores? So due to limited time, I'm only going to give a very high level overview of our data structure for maintaining the leverage score. So our data structure is a multi-layered one. So there are 3 layers. The bottom level, which is the arrows are in blue. So the bottom level is the true vector W, which we want to approximate. The top 3 layers are our approximation, which is our data structure. So the top layer, we call it the inner layer. The middle layer, we call it middle layer. And this orange layer, we call it the outer layer. So roughly, the inner layer makes an update whenever W gets updated. It runs faster but has a larger error. So roughly after polylog steps, the inner layer's error would already blow up. So the middle layer runs slightly slower than n squared time, but has a smaller error. And the outer layer is the slowest, but is the most accurate. And the outer layer can last for n to the omega minus 2 steps, which is enough for us to recompute after this number of steps. So roughly the inner layer takes 1 step after each update on the real vector W. After a certain number of inner layer updates, when the error is going to blow up, the middle layer is going to make 1 step. And it's going to get a much better estimation of the lever score, and it will refine, using this refine sigma in function, to refine the lever score approximation at the inner layer. When the middle layer takes a certain number of steps and the error is going to blow up, the outer layer will take 1 step and obtains a much better, much more accurate approximation of lever score, and it will refine the lever score approximation at both the middle layer and the inner layer. And when the outer layer takes more than n to the omega minus 2, slightly more than n to the omega minus 2 steps, we can afford to recompute everything. So that's basically the data structure. So interestingly, these 3 layers uses fast rectangular matrix multiplication for different sizes of matrices. We'll see a little bit more details in the next slide. And this layered structure introduces one more technical hurdle, which is, so while the inner layer sees every update of W, both the middle and outer layer only makes 1 step after a certain number of updates on W. So in fact, they see a sequence of W updates. And we introduced this batch low rank update technique to handle this this entire sequence by decoupling them into a heavy update and a heavy update which has low rank, and small update which has small size. So let's briefly talk about matrix multiplication. So the first role of this table is the exponent of matrix multiplication. So let's say tau mat nRn denote the time of multiplying n by r matrix with another r by m matrix. So when r is n, we know the runtime is n to the omega plus little o1, and this is called matrix exponent of matrix multiplication. When r is n to the 0.31, the runtime can be n to the 2 plus little o1. This number 0.31 is called the dual exponent of matrix multiplication. But we also need to use the following old result. When n is 0.17, the runtime becomes n squared log n squared. There's no name for that. Let's maybe call it third exponent or something. For r equals to poly log n, the runtime of this multiplication can be done in n squared time. So Vaidya's cutting plane method only uses the first row, which is the exponent. That's how they get n to the omega plus 1 log kappa. And Cohen Lee Song in 2019, their improvement on the LP algorithm uses the first and second row. But our cutting plane method need to use the entire table. So roughly the inner, middle, and outer layer corresponds to the last 3 rows of this table. And so using this connection with matrix multiplication, we can show that if one can get a better matrix multiplication result, then we can get a deterministic cutting plane method. So roughly, if one can multiply n by n to the 2/3 times an n to the 2/3 by m matrix in n squared poly log n time, then there is a deterministic cutting plane method which runs in time, which makes n runs in the same time. So let's briefly recall, we proved that there's a cutting plane method which runs in time, makes n squared log kappa calls with separation oracle with an extra runtime of n cubed log kappa. So classically, the cutting plane method only works for a convex setting, for example, linear programming, semi-definite programming, matrix intersection, etc. But for broader applications, especially for applications in computing market equilibrium, we generalize the result to convex-concave game setting, where we want to find epsilon approximate a stable point. We want to find epsilon approximate saddle point, and we achieve essentially the same runtime. So now let's introduce a few applications. The first one is the linear arrow debris market. So in this problem, we are given as input n agents, where each agent I has a unit of divisible good Gi and utility Uij for each good Gj. And the output we want to compute is a set of prices P for each one of the goods, and allocations for the agents. Basically, allocations means how much each agent sells his good to other agent. So what is a good price and allocation, right? This is called the market equilibrium. So the market equilibrium is the price and is the pair of prices and allocations which satisfy a certain desirable property. So first of all, prices are positive. No one wants to give out their good for free. Second, each good is fully sold. And each agent, the amount of money you get from selling his own item is equal to the amount of money he paid for buying other agents' items. And also, agent I only buys goods that attain the best bound per bucks. So the so-called best bound per bucks means that among all the good he purchases, basically among all the good where the allocations is non-zero, he only buys those that maximizes the utility, his utility over the price. So if he buys an item that is really desirable, he's not going to pay any money to items that are less desirable. So I'm not being very, I'm not going to formalize what these statements mean in terms of the math. So it's well known that market equilibrium always exists. And the question we study is how to compute a market equilibrium. This is a well-studied problem that there's a long sequence of previous work. The previous best work achieves a weekly runtime of n⁶ log nu and a strongly polynomial time of mn9 log n squared. So our result achieves a runtime of mn squared log nu, where here m is the number of possible transactions. One can think of m as being just n squared. So our result basically n⁴ log nu. U is the largest number in the problem. And so interestingly, while previous algorithms are specialized to this market equilibrium problem, our result is achieved by our cutting plane method, which is pretty general, which is generic tool. It's a similar problem called the Fisher market, where the buyer and the seller are separated. We also achieve improved runtime using our cutting plane method for convex-concave games. That's basically everything I want to talk about. Thank you for your attention.